All right, guys. So let's talk a little bit about the amino acids that compose the vast majority of the proteins that we're going to be interested in as we think about biochemistry. Now, hopefully, this is mostly going to be review for you guys, that you'll have seen a lot of this before, but you really do need to learn. And when I say learn in this context, I mean basically memorize these structures and properties of the key 20 amino acids. And the reason for that is that if you think about protein biochemistry as a language, and in a lot of ways shares some similarities, you think about that, the amino acids are the alphabet. You've got to know the characters in order to read the language, right? So this is kind of an important thing. So let's start right at the beginning, thinking about what amino acids look like. So you guys all hopefully remember that basic amino acid structure is sort of centered on a central carbon, which there is an amino group, a carboxyl group, a proton, right, and a so-called side chain, which we'll just label with an R for now, right? So that central carbon is, of course, known as the alpha carbon, and amino acids are then, of course, known as alpha amino acids because reference to that carboxylate group here, the next carbon over relative to the most oxidized carbon, in this case is that carboxylate carbon, it's like I said, is known as the alpha carbon, and it has an amino group on it, right? Therefore, it is an alpha amino acid, right? There's an interesting question for you. Could you have a beta amino acid? Sure, you could. You could have an amino acid that was, somehow, written like this, where you had a CH, NH2, CH2, CO minus, right? So then we would have an alpha and then beta amino acid. Now, for all the proteins and structures we're going to be thinking about, there aren't any beta amino acids to worry about, right? But it's just a matter of like re-referencing you guys with respect to that naming scheme of alpha amino acids, why they're called that. Okay, now for the amino acids, what distinguishes them, where they really are going to get their properties, is going to be in the identity of the side chain, which you guys hopefully will remember. We'll come to those in a moment. But for a second, let's think again about this alpha amino group and that alpha carboxylate group. What are those? Specifically, sort of general chemical properties those have relative to a discussion we were just having recently. You guys remember? Those are, of course, weak acid. In this case, it's a weak acid. And that amino group is a weak base, right? So both that carboxyl and that amino group, of course, can take up and give off protons, which means the ionization state of amino acids is a sensitive function, right? Is a sensitive function of the pH of the solution, right? So in thinking about amino acid structure and protein structure, we got to fold into that the equilibria of these weak acid and base groups that affect their structure and affect their properties. Okay, so let's start thinking about some of these properties of where these weak acid and base properties would matter. To begin with, let's just take the simplest possible amino acids, or amino acid, where that R group is a proton, it's a hydrogen atom, which is, of course, we'll get back to this, that's, of course, glycine, if you remember, right? And let's see what happens as we start varying the pH, right? This is something, again, that's hopefully mostly review for you guys. So you guys are going to remember that at low pH, say at pH 1, relative to the pKs of those weak acid and base groups, the alpha amino group and the carboxylate group, you kind of hopefully remember about where those are, right? So at low pH, both of those groups are going to be protonated. And when they're protonated, the carboxylate group is, of course, neutral, and that alpha amino group is then carrying a positive charge. This is therefore known as the cationic state of the amino acid. It's positively charged. Okay, so how about if we raise the pH, right? And the pK of that alpha amino group is going to be somewhere between 2 and 3, right? And as we raise the pH, that carboxylate group is going to deprotonate. We're going to get the ionized form of the carboxylate, which now, of course, has a negative charge. But that negative charge is, of course, balanced by the positive charge on the alpha amino group. So even though this molecule carries two charges, they're exactly the opposite sign. So the overall charge state of the amino acid, though ionized, is now neutral. This is also known as the Zwitter ionic form of the amino acid. And we can keep going, of course. We can increase the pH again. Now we get up above the pK of that weak base of that primary amine. It will now deprotonate. It's now neutral, but we look again, of course, that carboxylate group, since we exceeded its equilibrium constant, its pK, down here around 2 to 3, that guy still is negatively charged, still carries a negative charge, and this is, of course, the anionic or negatively charged state of the amino acid. Okay, now hopefully you guys remember most of that. There are a couple other things to keep in mind. Sometimes you will hear amino acids referred to as in a general class of biomolecules known as amphylites. Right. And an amphyolite is simply a molecule with multiple ionizable groups on it. You may hear people say that, and they come in handy for all kinds of different things, in addition to making proteins. There's one other important thing to note. The pH at which the amino acid is Zwitter ionic is, of course, the pH at which the protein sits at its pi, or its isoelectric point. Right? The point at which the amino acid carries no charge, right? Okay, so there are some other interesting consequences for this. If you think about titrating an amino acid, again, like glycine, right? If you think about going through the full titration, here again at low pH, we have the protonated form of both the alpha amino group and the carboxylate group. We start raising the pH, right? We get it to about half an equivalent of added, in this case, we'd be adding base. And we see that classic, like I talked about before with the Henderson-Hasselbalch equation, that classic flattening out of that curve as those hydroxyl groups get soaked up into the acid-base equilibria of that carboxylate group, right? And as for a significant increase in hydroxyls, the pH doesn't change much, and we hit that inflection point, right? And right at that sort of horizontal inflection point here is, of course, the pK, the pK of that alpha amino group. Okay, we keep adding hydroxyl equivalents. The pH starts to take off again. We get outside the buffering capacity of that carboxylate group, right at that central point. Oops, right? Stop it. We hit then, we hit, of course, the point at which the pH, this Zwitter ionic form, the dual charge form of the amino acid is present, right at the pi. And we keep going and keep adding hydroxyl equivalents. And again, we hit a second plateau. And this is, of course, the acid-base equilibrium for the alpha amino group, right? And there again, at its horizontal inflection is the pK of that alpha amino group, right? Okay. So there are a set of other properties that we need to think about with respect to the alpha amino acids, right? So if you go back for a second to this basic structure of an amino acid, right? And you look at the substituents around that carbon, there's something you should notice immediately for all the amino acids that we're going to think about, with one exception, and it's exactly the one that I've written up here, glycine. For all the rest of the amino acids we're going to worry about, there are 4 different groups around that alpha carbon, right? they're all going to be different, again, with the exception of glycine, right? So if you have a carbon atom with 4 different groups around it, you probably and hopefully remember from your basic organic chemistry that because of the bonding structure, the tetrahedral bonding structure of a carbon, if all those groups are distinct, you end up with a carbon that shows chirality, right? So when the 4 different groups are 4 groups around the carbon are different, you end up with a structure. You end up with a molecule or an atom, basically, that has, in principle, 2 different forms, depending on how you arrange those substituents, but they're mirror images of each other, right? Just like your hands are mirror images of each other. You cannot arrange them on top of each other in direct projection because of the asymmetry of the top and bottom of your hand. The same thing applies when you think about the nature of this tetrahedral bonding organization. There's no way to take this so-called enantiomer, all right, stereoisomer or enantiomer, as it's called here, and line one of these substituents up over here and get all the other substituents to be in the same place. It's sort of the nature of the spatial asymmetry of a chiral carbon, right? So all the amino acids except for one, glycine, is chiral, right? And that has all kinds of important consequences for protein structure, right? One of them, right, or one that you're going to hear a lot, I bring it up mainly because you hear the terminology, it's worth knowing where that comes from, is that chiral molecules have a tendency to do something called the rotating plane polarized light. It has to do with the asymmetric distribution of electrons around that central carbon. If you take a solution of those molecules and you pass plane polarized light into that solution, they will tend to rotate the plane of polarization. It's an old observation, goes back to the 19th century, 18th century, and where this was first observed. And one of the first molecules this was observed in was small molecules like this one, glyceraldehyde, all right, here. So if you look at glyceraldehyde, you have this aldehyde group, right? And you have this alcohol group, and then a proton and a hydroxyl group, right? Okay, 4 different substituents, right? They're not the same, therefore glyceraldehyde is chiral. And you have 2 different enantiomers of that glyceraldehyde, that chiral glyceraldehyde, depending upon, if you, again, you reference the aldehyde group here at the top, keep the alcohol here at the bottom, right? You have 2 different ways in which you have the hydroxyl on the right or on the left, right? But they're mirror images of each other. And if you take solutions of one form of pure form of glyceraldehyde, one pure enantiomer of glyceraldehyde, you pass plane polarized light through it, it'll rotate it to the left. The other will rotate to the right. And that was given a name. It's known as levorotary, right? Or dextrorotary, right? For left or right. So that leads to a shorthand, which is something L-glyceraldehyde or D-glyceraldehyde. And the same nomenclature has been applied to the amino acids. But here's the wrinkle. It's applied with reference to the structure of glyceraldehyde, not to the plane of polarization, right? So if you look here again is glyceraldehyde, there's that that aldehyde group. So if we put the most oxidized carbon in the same position as that aldehyde in glyceraldehyde for an alpha amino acid, that'd be the carboxylate group, right? And then if we now position the alpha amino group, right, in the same position as the alcohol group, we get what is an L amino acid, because the structure essentially mimics. The proton is now on the same side of the structure. It's on the right with the most oxidized carbon up in this Fisher projection. And so that looks basically kind of like L-glyceraldehyde, right, in terms of the position of the asymmetric substituents. So that's what these were called. This sort of enantiomer of the amino acids was known as an L-alpha amino acid. Well, the wrinkle is that that has nothing to do with the plane of polarization rotation by pure enantiomers of amino acids, L amino acids. In fact, a large fraction, most of the L amino acids are dextrorotary, right? So don't think that L amino acids means that levorotary. They're not. Most of them are dextrorotary. The L is with respect to glyceraldehyde. But this means we have D and L amino acids. And we'll come back to that in a minute because it has big implications for the conformational properties of amino acids made from either L or D amino acids. Okay, so essentially all the proteins we're going to care about, right? The vast majority of the proteins we're going to care about are made of L amino acids, right? All the proteins that are made, synthesized off the ribosome, initially are made with L amino acids. There's some fascinating examples where L amino acids that are encoded in the messenger RNA are subsequently isomerized by enzymes, special enzymes that flip the enantiomeric nature of the amino acid from L to D. And there's some non-ribosomal systems that use D amino acids quite specifically. But off the ribosome, we're going to use exclusively L amino acids. And the reasons I mentioned a second ago that this matters, if you look at an L-alanine, for example, we'll come to that again in a second, you put that carboxylate group in the same position relative to a D amino acid, you go up to the alpha carbon. Now look what happens to the positioning of the amino group in the side chain because of the asymmetry. In the one case, the side chain, which is this methyl group, goes off to the left. In the case of D amino acids, it goes off to the right, which means the spatial organization of the substituents of a protein made from D and L amino acids is a mirror image. And that has all kinds of important implications in biology when you're trying to bind asymmetric surfaces or other small molecules, right? Okay, so as I said, essentially all the proteins that we're gonna worry about, that are made off the ribosome are going to be made from the same 20 amino acids, right? There's some wrinkles, there's some post-translational modifications, some of them are quite fancy, but we're not going to have time to deal with that very much, a little bit, but not too much. So we're going to think about these core 20 amino acids that are the primary alphabet of protein biochemistry. And I'm going to break them down into 7 categories that help me remember them based upon their basic properties. But first, I want to mention some of the things you guys need to know, or you need to learn, or you need to memorize. Again, like I said, this is the alphabet of protein biochemistry. And so there are things I'm going to expect you to know that you just need to know to be a functioning biochemist with respect to the amino acids, right? And the things you need to know, right? Certainly in this class, you need to know the structures. If you don't know the molecular structures of the amino acids, learn them now, right? I know you may have learned them when you were an undergraduate. I know you're going to learn them again, and you'll probably forget some of them, and then you're going to have to learn them again someday, especially when you teach. But the more you do it, the faster you're going to hold on to them. And knowing those structures gives you the facility to think about proteins and biochemistry in a really important way. Okay. Second, you need to know their names, right? Their full names, sort of written out. You need to know the 3-letter codes. Those are pretty easy. But then you also need to know the 1-letter codes, because you're going to see all of those get used and mixed up, right? And some of them are obvious and some of them not so much, right? So you need to learn those. Okay. Third, you need to learn the pKs of the critical groups. You know, the alpha amino group, the alpha carboxylate group. You need to know the pKs of those groups in general. And it's interesting, right? You look in a textbook, you're going to find that they're not all exactly the same, right? They're going to change a little bit. Probably worth thinking about why that would be the case. We can talk about that a little bit later. You also need to know the pKs of the side chains that have ionizable groups, right? You need to have a reasonable idea of those side chain pKs, right? Which ones have ionizable groups and roughly what they are, right? And finally, fourth, you need to learn something about the basic properties. And this is in part related to whether they're ionizable or not, but not only, right? So one of the ways that helps me remember the different amino acid properties is I group them into sort of like 7 categories. The first is a set of aliphatic amino acids. Second, there are some aromatic amino acids. Third, cyclic amino acid. sulfur-containing amino acids, hydroxyl-containing amino acids, acidic amino acids, and their amides, specifically carboxylate-containing amino acids and their amides, and finally, basic amino acids. And one of the reasons I like to categorize in this way is because it gives you a rough scale for one of the key properties, which is hydrophobicity. Right up here around the aliphatic and aromatic amino acids, you're going to have the most hydrophobic amino acids, and then roughly as you go down the scale, and this isn't quite perfect, it kind of zigs and zags a little bit. I'll mention some of those, but as you come down the scale towards the hydroxyl-containing, acidic, amide-containing, and basic, you basically transition from highly hydrophobic to sort of like squishy hydrophobic to polar to ionized and quite polar. Right, so that's a hierarchy you want to keep in mind. Okay, so let's just go through these. Hopefully, again, a lot of this is a reminder, but these are some of the properties that you really need to know. If you're not familiar with them, now's your chance to refamiliarize yourself. All right, so the aliphatic amino acids, we got a series of these. There again is that basic alpha amino structure. There's that central carbon, there's that alpha proton, that alpha carboxylate group, and that amino group. And the simplest amino acid, which I already introduced to you guys, you just put another proton there, and that's glycine. And of course, we can see that glycine, now written out this way, is clearly non-chiral because two of these substituents, two protons, are exactly the same. But if we replace that proton now with a methyl group, we get the next larger amino acid. This is, of course, alanine, a single methyl group. If we replace that methyl group with a methylene and then branch at that carbon to put two additional methyl groups on there, we now have valine. All right, so these are sometimes known as sort of branched amino acids, right? You have alpha branched and beta branched. I'll show you an example of an alpha branched, a beta branched in a minute, right? Okay, here's the example. So if you replace that methylene group, right, in valine, you extend a methylene group, right, in between the alpha carbon, right, and that branch point, you now have, relative to the alpha carbon, right, this would be alpha to the alpha carbon, and then beta, and then put in a branch point, you now have leucine, right? And if we then go a little fancier and we take that same structure, similar structure to leucine, we pull off one of the hydrogens and we stick on a methyl group right there at the second carbon, right? And we then extend, instead of a branch point, we move the methylene to the other side of that carbon. We now have a 3-carbon chain with a branch point at, at the beta point, right? So the valine and isoleucine are both beta branched amino acids. Leucine would technically be delta. This is alpha, beta, delta, right? We now have isoleucine, right? Okay, so glycine to isoleucine, that aliphatic chain, it looks kind of like oil. It's getting a little bit longer, it gets. These are getting more and more hydrophobic, right? So the tendency of these amino acids to want to be in hydrophobic in solvent increases, right, as the length of these aliphatic chains gets longer, and that property begins to outweigh the ionizing or polar nature of those alpha amino and carboxylate groups, right? So the hydrophobicity scale of these guys kind of slews from left to right the way I have them on the slide. So here's a question for you. If you think about chemistry, thinking about doing chemistry, carrying out chemical reactions, are any of those amino acids going to be good for doing chemistry? Think about what you remember from your basic organic chemistry about driving chemical reactions, right? Needing to set up an energetic potential with a good base, a good nucleophile, or a good electrophile, something that's good electron withdrawing, electron donating. Answer is no, right? These amino acids in general, you're never going to really run into doing chemistry. They will sometimes, in special circumstances, get modified or hydroxylated. But for our purpose, you can think of our purposes in this class, you can basically think of them as inert under none of the sort of conditions of basic intermediary metabolism. Do you see these amino acids be reactive, right? They're also, because of their hydrophobicity, they're going to be found in the core of a protein. When we talk about protein structure, you'll understand a bit more why. These are hydrophobic enough, they're not going to want to be in water, right? So they're going to end up being found on the interior of proteins in most cases.